So welcome to Everything Matters, Tales from the Periodic Table. Tonight we're going to explore magnesium, the 12th element. This is our 12th Everything Matters, Tales from the Periodic Table. It's, I think, our talk with the longest title. And we will continue this until we get to the end. And I think that's going to be in about 8 years and 7 months, assuming that we don't take any breaks during the summer, which we do, which extends it out even. I'll be in my 70s by the time we finish this. That's job insurance, right? So I hope everybody has their collectible card for magnesium. How many people here have cards from previous Everything Matters that have been to previous? Okay. If you want to fill in your collection, on the table over there, you can fill in your collection. And I notice, okay, don't worry, they're still there. We'll make sure that you can fill in your collection, because there's only 102 more of these, 106 more of these to go. So everything starting from hydrogen is over there right now. Let me see what we got here. So I'm your host, Ron Hipschman. And I'm going to talk a little bit about the chemistry and physics of magnesium and how it's essential to sustain life on Earth here. And I'm going to be followed by Eric Muller, who's standing over there. And Eric Muller's, he's a senior science and math educator here in our Teacher Institute. We train teachers here. It's one of those little hidden things about the Exploratorium that not a lot of the public knows. We train how many teachers a year? About bunches. That's a big number. Not Avogadro's number, though. Oh, okay. And he teaches workshops here and all over the place, all around the world. And tonight, Eric is going to show how much magnesium wants to burn. It wants to burn so much, you can actually burn magnesium in carbon dioxide. And we're going to do that because we can't make smoke here, because we have very good smoke detectors in the Exploratorium. We're going to go around the curtain and out the door over here after I'm done, and Eric's going to do a demonstration outside of magnesium burning inside of dry ice. It's really an amazing demo, so I hope you stick around and see that. So, magnesium. Let's go to our periodic table. This is, again, wonderful periodic table, by the way. Theodore Gray does this periodic table. He has books and cards and posters and placemats and all this wonderful set, and a website called periodictable.com. He even has a periodic table, by the way. It's amazing. It's a really cool thing. I kind of stole this from him, and I want to give him credit, and I want you to go out and buy his stuff because it's really good. Magnesium, up there in the third row, is the 12th element. And it is chemical symbol Mg. And the 12 there, just to review, is how many protons are in the nucleus. There are variable numbers of neutrons, but there's 12, and that identifies that atom as magnesium. Magnesium got its name sort of from one of the areas in which it was discovered. It was discovered in Greece, near Thessaly, in a prefecture called Magnesia. Magnesium. Here it is. It's sort of in the center of the map there. We can zoom in, I guess. Let's zoom into the center there. We'll see the prefecture of Magnesia. There we go. Not a very nice bay there. And it's given its name not only to the element, magnesium, but it's also given its name to a different element, manganese, and to something else that's found near there, magnetite. Here's crystals of magnetite, and you can come up and here's a sort of the same kind of sample. You come up and see that later. These are iron oxide, and it has no magnesium in it. But that's where we get our term for magnets, because magnetite, here's another piece of magnetite, this isn't a crystal form, takes on the magnetic field of the Earth. It kind of freezes the magnetic field of the Earth when it's made, and these are magnetic. They're also called lodestone. When this stuff gets ground down, when this stuff gets ground down, it forms this black sand that we find on our beach. at an ocean beach. If you go out to Ocean Beach, you'll often find these stretches of really, really dark sand, look like this. And that dark sand actually is this thing ground up. It's if you take a magnet to Ocean Beach and stick a magnet in the sand, you would draw out of the sand magnetite. And so really, we use this black sand in our exhibits. We actually go out to Ocean Beach and collect some buckets of it. We have permission to do that because it's the GGNRA. And we use it in our black sand exhibit, but that's all magnetite. Actually, you could probably attract it with magnetite. Yes, you can. Come up and play later. But that has no magnesium in it. So moving along. I had to say, it's going to be a while before we get to iron, okay? So, preview. It was first purified by this guy, who we've seen a lot in the last few months. He's been responsible for a lot of the elements that we've seen, lithium and sodium and a lot of the others that we've seen recently, Sir Humphrey Davy, and he first isolated magnesium in 1808. He used electrolysis to do that, when we saw that last month. He suggested the name magnium for this element. Didn't stick, I guess. So here we are. Here, the column that magnesium is in is the alkaline earth metals. We've already seen one of those. We've done one, beryllium, up above it. But magnesium there in the third row down is, again, element number 12. And it's a little bit different than what we saw last month. Sodium, we'll get to that in just a moment. It's a pretty common element. If we actually shaped these squares of all the elements and made their size something equivalent to their abundance in the Earth's crust, we'd get an element table that looks sort of like this. See, all the elements that we've been working on so far, high up on the table, all these ones at the top of the table here are all pretty common. There's a few that are not, like lithium is not very common and beryllium is not very common. But here's magnesium right here, pretty common element. Let's look at that, actually. So if we look, for instance, in the universe, it's actually a pretty common element in the universe. It's about the 9th most abundant element in the universe. And I'm marking magnesium with the blue line. So you can see it's really high up there in abundance. In the sun, it's similar to what it is in the universe, which is actually not surprising. If you look at it in the crust of the Earth, it's actually the 6th most abundant element in the crust of the Earth. It's very, very common. As a matter of fact, it makes up 13% of the Earth's mass. That's pretty high. It's about the 5th most abundant in the oceans. It's the 4th most abundant if you talk about dissolved things. So it's very abundant in the oceans. And even in humans, it's not bad. It's the 11th most abundant thing in human beings. It forms a very important part of our biology. So if we look at, I mentioned the fact that 12 protons are in the nucleus of magnesium, but different numbers of neutrons. If you have different numbers of neutrons but the same number of protons, it's the same element. And we call those same things, they're same but different, we call them isotopes. And here are all the isotopes of magnesium. There's a lot of them. But only 3 of them are not radioactive. Only 3 of them are stable, 24, 25, and 26. Those numbers are the total number of things, protons plus neutrons, in the nucleus. So magnesium 24 has 24 total particles, which means 12 protons and 12 neutrons. Magnesium 25, 12 protons and 13 neutrons, and magnesium 26, 12 protons and 14 neutrons. Hello? Oh, there we go. Those are isotopes. Those occur in different abundances in the universe. Magnesium 24 is the most abundant, but the other ones are actually pretty good. I mean, often you'll have 0.000% on some of those isotopes, but these are actually all pretty common. With magnesium 24 being the most common. Now, the coolest thing about magnesium is the density of magnesium. And so the density of magnesium is only like 1.7 grams per cubic centimeter, where water is 1. gram per cubic centimeter. So it's a little denser than water, so it's going to sink in water. But if you come up here and you want to play around a little bit, I have some blocks that are different materials. So I had to make up chemical symbols, by the way, for the first two blocks here, because this is maple, so it's Ma, and this is plastic, so it's Pl. But magnesium and the rest of them have their own chemical symbols. And magnesium is actually very, very light, undense. What do you say was undense? There's no word for that. I'll pass these around. These are solid blocks of magnesium. So I'll pass those around so you can see how light they are. But come on up after and compare it to aluminum and iron and lead. Lead's really dense. And if you really want to be very careful if you do this, but I don't have the same size block, but this is tungsten, which is almost double the density of lead, the same density as gold. This is actually quite amazing to try and lift, but be careful, it has sharp edges, and if you drop it on your foot, it will leave a mark. So come up and try that after. Actually, I have a chart here sort of showing the density. So there's magnesium this is in order of elements. So it's hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, all the gases. Oops, let me turn that little light on there. All the gases right here, they have very low densities. Then we start building up, and right there is magnesium. Next month, aluminum is a little denser, not much. Magnesium is about 2/3 as dense as aluminum. And then you come back down when you get to the gases again. But you see that magnesium is a very low density element compared to the rest of the periodic table, where they just get heavier and heavier and heavier. If you list them instead of by atomic number, if you list it by density, then you can see something like this. And here, magnesium is way down at the bottom of all the elements. The densest element, there we go. The densest element is way up here. Osmium and iridium are very, very dense. I don't have chunks of those, sorry. They're very expensive or toxic. But you can come over here later on and compare these densities. We do have some safe things here, so you can check out tungsten, lead, iron, aluminum, magnesium, and I can't do maple and plastic because they're not on the table of elements, but they're labeled. Magnesium is made in very large stars. As you can see, the square over there, green, made in very large stars. It's made by an interesting process where you start off with a carbon atom. Carbons have 6 protons and 12 total particles, so 6 and 6. 6 protons, 6 neutrons, and you add to that 3 successive times. You add a helium nucleus, and another helium nucleus, and another helium nucleus, and you notice that adds up to 12 plus 4 plus 4 plus 4, 24, and 6 plus 2 plus 2 plus 2, 12. So you end up with magnesium 24. With 12 protons. That's the process, but it only happens in big stars, and big stars tend to end their lives spectacularly. They blow up, and they spread that magnesium out into the interstellar medium, and then other stars form from that. Our sun did, which is why we have so much magnesium. We were formed out of the gas ejected from previous stars that had blown up. So that's a big picture. Let's go to the small picture. Last month we did sodium. And sodium was kind of unique because it had all of its shells filled except for the outer shell, which had just one lonely electron in it. All these other spaces available. Just one electron. It wanted to give that electron away really desperately. So, magnesium is similar, except magnesium has 2 electrons in the outer shell. It'd like to get rid of both of those electrons. So when it does chemistry a little different than sodium did. If we look at the atom itself, again looking small, we've been comparing all along the size of hydrogen compared to all the other elements. So here's hydrogen again, and magnesium is a very large atom compared to hydrogen because it has those extra electrons sort of flailing off out on the outer orbitals. It has a spectrum that's also interesting too. I found another periodic, really another good, cool periodic table here. I found a periodic table of the spectra. So here you see the spectrum of all the elements. Let's just bring magnesium out there. And you can see that magnesium has a very bright green line. Let's just look at that a little closer. So there you can see it has a very bright green line, sort of in the middle of the spectrum there. That bright green line, I could give that name, today would be appropriate to give that a name, wouldn't it? Let's just call it shamrock green, okay? Yeah. I had to use the special effects a little bit here. If you look at the solar spectrum, instead of having the colors glow, the solar spectrum is an absorption spectrum, and you can see, now this is if I wanted to make a really long spectrum, this would be hundreds of feet long, but you've stacked them all on top of each other. So this is the full spectrum, but stacked. And the magnesium lines you can see right there, there, and there. Those are the green that you saw on the previous slide. They're very close. They're fairly close together normally, but in this thing, since it's so spread apart, since it's so long, you can see them individually. They're very, very, very dark lines in the solar spectrum, very easy to see. There are other dark lines that were easy to see in the solar spectrum, which are abundant elements in the atmosphere of the sun. This big dark one up here, that's hydrogen. This was last month's sodium. Very in the solar spectrum. That's also hydrogen right there, and that's hydrogen right there as well. But there's a lot of really interesting things you can see. You learn a lot by looking at the sun. As a matter of fact, you know, helium was discovered on the sun before it was discovered on Earth, because they found one of those dark lines that they couldn't explain. That's why it's called helium, after Helios, the sun god. So where do we find magnesium where we are always, from our vantage point here, where do we see magnesium? It's on the table here. Of course, we see it in milk of, yes, Magnesia, named after the prefecture. And that really is magnesium hydroxide, MgOH2. Where else? I have them right here. You've also may be familiar with Epsom salts. Is anyone soak in Epsom salts anymore? Really? Does it help? I always wondered whether it's kind of like pseudoscience, but maybe. If it helps, I'm glad to hear that. It can also be used as a laxative, just like milk of magnesia. And this form of magnesium sulfate also is hydrated. It has lots of water attached to it. Where else have we seen mag? Well, there's mag wheels. Those used to be magnesium. However, we don't call them mags anymore. We're not supposed to call them mags because there's actually no magnesium in them. They're alloy wheels now, and they're actually, they're actually aluminum alloys. But that makes them lighter. So if you have a lighter wheel, it's easier to turn it. You can reduce fuel consumption. If the wheel is lighter, it can respond to the terrain more closely. It improves the grip. And so aluminum wheels, alloy wheels are actually quite helpful on cars. They don't use magnesium, pure magnesium for wheels anymore. They used to. And I think we're running out of batteries. Are we running out of batteries here? No. We're just getting radio interference. They used to make actual magnesium wheels for race cars, but magnesium reacts so much with the atmosphere and rain and water that it's not a good thing to use for wheels. They tarnish, they get brittle really quick, and so they don't use it for car wheels anymore. It cracks, it pits, it corrodes. So if you want to keep them looking nice too, that's not good. So magnesium, since it burns so brightly, as we will see, was also used in camera flashes. So here, you can see that there's a little pile of powder inside there. It has a wind-up thing. See the key on the bottom. And you would wind that thing up, push the button, and it would create sparks in there, and this thing go, and that's a really bright flash. If you don't set everything on fire, you can get a good picture. Some minerals that we I have up here, you can come and see, I have some serpentine. And we find this mineral around here a lot. Serpentine you can find like down in Crystal Springs Reservoir, and it's a metamorphic rock. It's has kind of a soapy texture to it. And these pieces here are also serpentine. So come up and feel this kind of soapy texture, greasy texture of this. Serpentine also is where we get asbestos from. Here's the form of that. Actinolite asbestos. This is the source for that substance of pain, suffering, and death. We don't use it much anymore, even though it's a wonderful insulator, and it insulates heat, it insulates electricity, but unfortunately it does cause severe problems in lungs. Magnesium is responsible for us being here as well, because plants use magnesium. This is a molecule of chlorophyll. And can you see the magnesium atom in there? See it? There it is. Okay, magnesium is right at the center of the chlorophyll molecule, and it's really responsible for allowing it to absorb sunlight, convert that sunlight into energy to be able to turn CO2 into oxygen and sugars. And so without that, without plants, we don't exist either. So we owe magnesium a great debt of gratitude. In us, it's used in us. It's 300 different biochemical reactions in the body use magnesium, helping to maintain nerve and muscle function. It helps support your immune system. It keeps your heart beating steadily. It helps keep bones strong. It also helps regulate blood glucose levels. And it actually does aid in the production of energy and proteins. So it forms a really important part of our diet. And we get most of our magnesium from vegetables, dark green leafy vegetables. So I guess you could take supplements, but there's really no need to. Just eat your vegetables. So with that, I want to turn it over to Eric, and yes, you. And you've all been waiting for this anyway. So this is the exciting part. Eric's going to take magnesium powder. It's much easier to light when it's broken up into particles like this. I grant you the powder.
Thank you.
And you can't light up this block of aluminum. It doesn't work unless you.
I bet we can make it work.
Eric might be able to. Eric is our king of fire here. When we do Iron Science Teacher during the summer, and every demo that Eric has in Iron Science Teacher has something to do with flames.
Questionable. Yeah.
We've had a harder time doing that here in this building, but
I get to light something on fire. Hey, by the way, is it a little stuffy in here? Yeah. I think we should get out of here.
Let's get out of here.
Yeah,
outside.
Go outside. Make sure you got your jackets on.